We saw that the first derivative shows where a function increases or decreases, and the first derivative test lets us use that information to determine local max and local min. Now we're on to concavity. The concavity, or the shape of a graph, is obtained from the second derivative. It is used to determine the rate at which a function increases or decreases, so like acceleration or deceleration. Let's put this in graph form. We'll start with f of x equals x squared, and we're going to compare that with the shape of g of x equals the square root of x. We're going to plot some points. Let's start with f of x equals x squared. Make a t-chart. We'll label it x f of x. And let's go to the origin. So 0 squared is 0, which is the origin. And if I determine at x equals 1, 1 squared is 1. So we got 2 points for that graph. Let's plot some points for g of x equals the square root of x. We'll have a t-chart. We'll have x and then compute the g of x. If x is 0, the square root of 0 is also 0. And if x is 1, the square root of 1 turns out to be 1 as well. So we'll mark those points. Now, just looking at those two sets of ordered pairs for the x squared and the square root of x, we see that the graphs will be rising, and so they're increasing. The second derivative is going to show us how they're different, though. Before we get there, let's plot a few more points. So I want to plot some points for the x squared between 0 and 1. Let's begin with 0.25. So 0.25 squared, 0.0625, 0.5, 0.5 squared is 0.25, and we'll go up another quarter step of a unit. So that would be 0.75, and we're just going to round that. So 0.75 squared is 0.56. We're going to eyeball these distances. So I'll start at 0.5, that's 1/4, and then try to gauge what the other distances look like. Quarter of the way through, it's still pretty close to 0, and at 0.75, it's not that much more than a half. So connecting those dots, we get that picture of the parabola. Let's plot some points for the square root. Quarter of the way, the square root of 0.25 is 0.5. The square root of 0.5, we'll round it, is close to 0.71. And the square root of 0.75 is about 0.87. So I'll go half between 0 and 1 and then split the half. Same thing for the vertical. And we'll start plotting points. At 1/4, that's 0.25, takes us to a half. At 0.5, it's about 0.71, and at 0.75, it's 0.89. We connect those, and notice that it's increasing, but the shape is rather different on both of these, right? For the x squared, where it looks like it's a bowl that faces up, we call that shape concave up. And for the shape of the square root function, looks like an open umbrella, we call that shape concave down. Now we're going to look at the derivative values. Let's look at f of x and find the derivative. That would be f prime of x equals 2x. And we will evaluate the derivative at each of 0.25, 0.5, 0.75, and 1. 2x. 2 times 0.25 is 0.5. 2 times 0.5 is 1. 2 times 0.75 is 1.5, and 2 times 1 is 2. Notice here that the first derivative values are positive, 0.5, 1, 1.5, and 2. So now we're also looking at the numbers. The fact that they're positive tells us that function increases, but the other thing to notice is that the particular derivative values, the first derivative is increasing. Concave up, first derivative is increasing. Let's see what happens with the derivative of g. We compute the derivative, g prime of x, that'll be 1/2, and in the denominator, x to the 1/2. We'll get decimal approximation. The first one's easy. At 0.25, you get 1. At 0.5, 0.71. At 0.75, 0.58, and at 1, so that would be 1/2 times the square root of 1 is just going to be 0.5. Let's notice the derivative of g evaluated at 0.25, 0.5, 0.75, and 1. They're all positive, which matches the fact that the graph of the function is rising. However, also note that the first derivative is decreasing. So where the first derivative is increasing, we have concave up. Where the first derivative is decreasing, we have concave down. And both of these functions are increasing in terms of shape. Now we can define concavity. Definition. Suppose f is differentiable on an interval I. The graph of f is concave up if and only if the derivative is increasing on that interval, and the graph of f is concave down if and only if the derivative is decreasing on that interval. The point where concavity changes directions is called an inflection point. Let's look at one. Let's suppose we have a graph that appears to be rising, and it still rises, but the shape changes. The point where concavity changes, so for the first graph we go from concave down to concave up. This is concave down. And the second portion we see is concave up. The point at which concavity changes is called an inflection point. Similarly, we could have a graph that starts concave down and then, say, changes directions. It might go down some more, but then goes back up, where it functions like an open umbrella. That region we call concave down, where it bowls up as though you can eat cereal out of it. We would call that concave up. And the point at which the graph of the function changes from concave down to concave up is what we call the inflection point. Example, find the intervals where f is concave up or concave down and locate any inflection points for f of x equals x to the 4th minus 4x cubed plus 12. Let's begin by listing the domain. The domain of f is the set of real numbers. Why? Because we are working with a polynomial function. Now, to determine concavity, we need the second derivative. Let's get the first derivative first, which would be bring the 4 down. So you got 4 times x to the power of 4 minus 1 is 3. Then minus the derivative of 4x cubed. Bringing the 3 down, you got 4 times 3 would be 12 times x to the power of 3 minus 1, which is 2. And the derivative of 12 is just 0. Now we can use that to find the second derivative. the derivative of 4x cubed. We need to bring the 3 down, multiply it to the 4, so that would be 12. X to the power of 3 minus 1 would be 2. And then take the derivative of 12 times x squared. Bring the 2 down from the power for the x, so you got 12 times 2. That would be minus 24. X to the 1. We want where the second derivative equals 0 or the second derivative is undefined. And that's not going to happen because the second derivative is a polynomial as well. We'll proceed to find where the second derivative function equals 0. We got 0 is equal to 12 x squared minus 24x. We can factor out a 12 and an x. Factor out a 12x from 12x squared. You still have 1x left. Factor out 12x from 24x, and we've got 2 left. So we've got 2 what I call candidates for inflection points. Those candidates are x equals 0 and x equals 2. And now we will make a number line sign chart for the second derivative, f double prime. Draw the number line, write x below, and we know that when x is 0, the second derivative is 0, and when x is 2, the second derivative is 0 as well. Take the second derivative, it's 12x squared minus 24x, and evaluate a number from each of the 3 intervals to determine the SIGN of the derivative. Let's do -1. F double prime at -1, 12 times -1 times -1 minus 2. So I will multiply positive, negative, and negative. That turns out to be positive. The interval less than 0 for the second derivative would be positive. Now let's evaluate the second derivative at a number between 0 and 2. So we'll do that at 1. So we got 12 times 1 times 1 minus 2. That's a positive times a positive times a negative. The product is a negative. Now let's evaluate the second derivative at, say, 3. That would be 12 times 3 times 3 minus 2. That looks like a product of 3 positive numbers. Positive times positive times positive is positive. So we'll mark that region as positive. What do we know by the definition of concavity? We know that if the second derivative is positive, it's concave up. The graph is concave up. If the second derivative is negative, the graph of the function is concave down. And if the sign of the second derivative is positive, then the graph is concave up in that region. So let's answer the question. F, the function, not the second derivative, not the first derivative, but the function f is concave up from -infinity to 0, and again from 2 to positive infinity, and f is concave down in between. That would be from 0 to 2. We were also asked to determine inflection points, if any, and we now see that f has inflection points at 2 ordered pairs. 0 f of 0 and 2 f of 2. Example, find any all inflection points of f of x equals the quantity x minus 1 raised to the power of 5/3. Let's begin by writing down the domain. The domain of f is the set of real numbers. Inflection points, what are they? Inflection points are where concavity changes directions. And how do you determine concavity? By finding the sign of the second derivative within particular regions. So let's begin that. We start by finding the first derivative. To do so, we bring down the 5/3. Then you still have x minus 1. And now you've got 5/3 minus 1, so that would be raised to the power of 2/3. Now let's find the second derivative, f double prime of x. That means take the derivative of the first derivative. So you had the 5/3. Now bring down the 2/3, and we have the x minus 1 raised to the power of 2/3 minus 1 is negative 1/3. Simplify that sum. We can write the second derivative, f double prime of x, is equal to 5 times 2 gives you a 10 in the numerator, and in the denominator 3 times 3 is 9. And let's move that expression that has a negative exponent in the numerator to down into the denominator. So we can write that as x minus 1 to the 1/3, no negative, in the denominator. We would have inflection points where the second derivative equals 0 or where the second derivative is undefined. We know that the second derivative does not exist at x equals 1. That's because that would give you a 0 in the denominator, and there is no place at all where the second derivative would equal 0 because the numerator is 10. Now let's make a number line sign chart for the second derivative. I'll write f double prime to indicate I'm looking for the sign of the second derivative, x below it to indicate that that's a particular x value. So when x is 1, the second derivative doesn't exist. We need to now evaluate for the sign of the second derivative in the region before and also in the region after 1. Let's do that. Second derivative, let's evaluate that at 0. That would be 10 in the numerator, 9 in the denominator, 0 minus 1 to the 1/3. The only number of consequence for us is the negative 1 to the 1/3, which tells you it's going to be negative. So the region to the left of 1, the second derivative is negative. Pick a number to the right of 1. Let's just do 2. Second derivative evaluated at 2. 10 in the numerator, 9 times 2 minus 1 to the 1/3. All three numbers are positive, so the product would just as well be positive. So that region to the right of 1, the second derivative is positive. Where the second derivative is negative, the graph of the function is concave down. Where the second derivative is positive, the graph of the function is concave up. So we have a point shown to us in the second derivative where concavity changes directions. Concavity changes directions at x equals 1. So the answer here is f, the function, not the derivative, not the second derivative, but the function f has an inflection point, and that ordered pair would be 1, and f evaluated at 1.